First, import your selected image in the top view using the Picture command. On a different layer, trace the main figures that will drive the distortion using polylines, not rounded or NURBS curves. Add additional segments to connect those frames and to extend them to the edges of the image, including tracing the perimeter of the image itself. Ideally, you want all the shapes created to be triangles or quadrilaterals. Now open Grasshopper. If you're not familiar with Grasshopper, it is a plugin that sits on top of Rhino and can reference the geometry that you draw in Rhino, but it does not automatically read the whole scene, only what you indicate. To reference drawn geometry, Grasshopper uses params, located in the first tab and the first toolbar, Geometry. Select the surface param and place it in the workspace, called the canvas. It will appear orange at first, which means that it is missing data. If you hover over the component, the tooltip menu will say Empty Surface Parameter. Right-click the component, click Set One Surface, and then select the image in the Rhino viewport. The surface param will turn gray, which means everything is normal. Do the same with a curve param, but this time select Set Multiple Curves, select all of your curves, and then hit Enter. A panel component can be used to read the output of a component so that it is not necessary to hover the mouse. It looks like a post-it note and is also under the Params tab, but in the Input toolbar at the right. I will use panels regularly to show the outputs on the screen, but they will not be necessary for any operations, simply for display convenience. In Grasshopper, inputs always enter on the left, outputs are always on the right. Every component either holds data, outputting the same information, or it operates on the input, outputting new information. Params are components that normally only hold data, so it is natural to have them at the beginning of an operation to hold the initial conditions, whether geometry, numeric parameters, or something else. Hide the Rhino layers now. In this sketch, we will want to convert the surface to a mesh, because a mesh, made of discrete faces, deforms along sharp edges. By linking each vertex of the mesh to a point in the image, deforming the mesh will also deform the image. There are many ways to convert a surface to a mesh. In fact, it is possible to simply connect the output node of the surface param to the input node of a mesh param. But in this case, the mesh should follow the curve network. A good method for this is called the Delaunay mesh. From Mesh tab and Triangulation toolbar, select Delaunay mesh. Be careful selecting here, as there are two options that are slightly different, and place it on the canvas. The inputs for this component are, first, a set of points, and second, a base plane. Notice the base plane already has a default value, the world XY plane. This doesn't need to be changed because the image is in the top viewport, so it is also parallel to the XY plane already. For the point input, we want to use all the curve points. Go to Curve tab and the Analysis toolbar. There is an endpoints component, but this will only give the start and end, not any corners within a polyline. A better choice is the Explode Curve component, which is in Utilities. This gives both line segments and vertices as outputs. Connecting the vertices output directly to the Delaunay input does not immediately work. Instead, it gives some overlapping meshes with few vertices and some insufficient point errors. To see why, connect the vertices to a panel. What this shows is a set of lists, one list for every curve input, with its vertex points separated from the other curve's vertex points. This is called a tree structure in Grasshopper. This is a confusing data structure at first, but it eventually becomes familiar. The purpose is to recognize that the data that is output from a list of multiple inputs often wants to be used for individual operations, like finding the average of each curve's vertices. Notice that the connecting wires also look different when there is a tree, dashed lines indicating the separations, compared to solid double lines for a list, or a single line for a single item. In this case, all the vertices need to be lumped together in a single list. This is called flattening the tree. It can be done with a component, or more easily by right-clicking on either input or output nodes. Use the V output in this case because there is one step that will be inserted before the Delaunay mesh is created. That step is to remove any duplicate points. To do this, use a component called cull duplicate points, and rather than hunting for it, a shortcut is to double-click on the canvas and type the component name in the search bar. Check carefully that you have the right component. Sometimes there are similarly named components. This will go in between the explode curve output and the Delaunay mesh input. This kind of flexibility to insert improved processes is one of the really great aspects of visual programming. Grasshopper is now displaying all of the geometry simultaneously. This will become a visual mess, so right-click on the earlier components and deselect the Preview button. This will change the component from light gray to dark gray. The components are still working, just not displaying. In case the Delaunay mesh is not showing or is just a wireframe, make sure that Grasshopper's preview mode is set to shaded not wireframe. In case the mesh just looks like a flat pink rectangle without triangulation, go to Display in the top row and enable Preview Mesh Edges.